So now that we've talked about derivatives, Chapter 4 is mostly about applications of derivatives. So how can we use this to do real-world problems? So Section 4.1 is Linear Approximations. The idea behind this section is that lines are a lot easier to work with than complicated functions. So what we're going to do is we're going to try to use lines instead of using other equations. That's the idea behind it, is that lines are easy. This entire semester we've been trying to find equations of lines. We've been trying to find tangent lines. So y equals mx plus b. And this is a much easier function to deal with than, say, a quadratic or a cubic or anything like that. So that's what we're going to be doing, is we're going to use the idea of tangent lines to approximate function values. So again, the idea here is we're going to use lines, more specifically we're going to use tangent lines to approximate function values. So that's what we're going to do. Now there are mostly two types of problems in this section. The first type is, what is a change in f of x? Now when we say change, we're talking about subtraction usually. So the first type of problem is, what is a change in f of x? In that case, we're going to use the notation that delta f, now it could be written as df. You'll see it both ways. What this means is a change in f. We're going to use that that's approximately f prime of a number times delta x. So whenever we see a problem that's talking about the change in f of x, we're going to use the fact that the change in f of x is approximately the derivative times the change in x. Now where is this coming from? Let's say here's my function, and here's a value a. If I want to know the approximate change in f, so that's talking about this value, that's the change in f, change in y values. If I want to know that change, what I can do is look at the tangent line. The tangent line here has slope, f prime of a. Here's my other value b, so the change here is delta x. We can say that this change is approximately the change in the tangent line. Well, the change in the tangent line is just the slope times how far along did I move on the x-axis. So that's what we're doing here, is we're saying the change in the real function is approximately the same as the change in the tangent line for relatively close values. Well, the change in the tangent line is the slope times the run, which is the change in x. So this is the function that we're going to use. And again, this is coming from the fact that we're looking at the change in the tangent line as opposed to the change in the curve or the change in the function. So that's the first question this section is going to ask you. The second part of this section is asking us to estimate values of f. So it's going to say something like, estimate the value of f at 2.2 or something like that. Whenever we're trying to estimate the values of f of x, what we're going to do is we're going to find the tangent line, which we're going to label as L of x. So this is the tangent line at an easy value of x, and then we're going to plug in. So the two problems in this section are the change in f, which is subtraction, or estimating the values of a function. Those are the two types. In the first case, we're going to use the fact that the change in f is approximately the slope of the tangent line times the change in x, which is the run. The other one, what we're going to do is to estimate values of x, values of f of x. We'll find the tangent line at a relatively easy value, and then we'll plug in what we want. Now the picture you want to kind of think for the second one. let's say this is my f of x here. Here's where I'm going to center it. I'm looking for the function value close to a. So I'm looking for this function value here. What I can do is just find the associated value on the tangent line, and that's a pretty good approximation. So that's what we're doing, is instead of trying to look on the curve, look on the tangent line. It's much easier to plug into a line than it is some complicated function. So that's why this is called linear approximations, is that we're looking for numbers using the tangent line, which are linear. Alright, so given those, let's see how we can actually do this. Example 1, let's let f of x be x squared. I want to know what is the approximate change in f of x from x equals 2 to x equals 2.1. So the first question to ask is, are we looking for a change in f of x, or are we trying to estimate the value of the function? Well, the problem says what is the approximate change in f of x. So the equation that we're going to use is that the change in f of x is approximately f prime of a times delta x. Okay, so now f prime of a, we want to set a equal to the number that's easier to plug in. So is it going to be easier to plug in 2 or 2.1 to a function? Well, definitely easier to plug in 2, so I'll set a is equal to 2. Now I need to know what is delta x. So this means as I move from 2 to 2.1, how far did I have to go? Well, I had to go positive 0.1. So that's my delta x. Now at this point all I have to do is plug it into my formula here. So the change in f is approximately f prime of 2 times 0.1. Now what is f prime of 2? Well, to figure out f prime of 2 you need the derivative. Using your power rule, it's just going to be 2x. So this is 2 times 2 times 0.1. So 4 times 0.1, which is 0.4. So what does that tell us? It tells us that going from x equals 2 to x equals 2.1, our function increases by approximately 0.4. So that's how we would kind of read this off. Let's do another one. Let's estimate 1 over 5.1 cubed minus 1 over 5. So again, the first question to ask here is, am I looking for the change in a function, or am I looking for a function value? Well, here we're talking about subtraction, so that's a change in a function value. So I'm going to be using this equation. The problem is, what is your function? We don't have a function here at all. Whoops, I meant to make this cubed. So what function are we actually plugging numbers into? Well, this is 1 over 5.1 cubed and 1 over 5 cubed, so I think our function here is 1 over x cubed. Okay, now I need to know an a and I need a delta x. So the two numbers are 5 and 5.1. So you want to ask yourself, which one is going to be easier to plug in, 5 or 5.1? Answer there is definitely 5. Going from 5 to 5.1, moving 0.1. So my change in x was 0.1. Alright. Now is when I just plug it into my formula, but to do that I need the derivative. So if I change this to be x to the negative 3, I'll get that my derivative is negative 3x to the minus 4. So the change in f is going to be approximately f prime of 5, so negative 3 times 5 to the negative 4 times 0.1. So what is negative 3 times 5 to the negative 4 times 0.1? I got that this is negative 0.00048. So a very, very small number. What this says is that the difference between 1 over 5.1 cubed minus 1 over 5 cubed is approximately negative 0.00048. So that's how we would read this off. Again, what did we do? We had a function. The problem didn't give us a function, but we made a function out of it. We had the starting point A, the difference in the two x values was 0.1, and we plugged it into our function, or our equation. Let's do one more of these. How much larger, and again we're just estimating here, how much larger is the square root of 4.2 than 2? So ask yourself, am I looking for a change in a function value, or am I looking for an actual function value? Well, this says how much larger, so that's talking about subtraction. So the real question here is estimate the square root of 4.2 minus 2. That's really what we're trying to do here. I'm going to write 2 slightly different. We had the square root of 4.2. 2 is the square root of 4 because now they look similar. So just like we did with the previous example, we're talking about the change in a function value. Well, I need a function if I'm going to do that. So what function does it look like I'm using here? Looks like the square root of x, which is x to the 1/2. Now I need a, and I need a delta x. So a, which one's going to be easier to plug in? 4 or 4.2? Definitely 4. And now how far do I move if I go from 4 to 4.2? I'm moving the positive direction, 0.2. Now just plug it in. So f prime of x is 1/2 x to the negative 1/2. So if I plug this in, I'm going to get, let's see, f prime of 4 was going to be 1/2 4 to the negative 1/2 times 0.2. 1/2, or 4 to the negative 1/2 times 1/2 is 0.25 times 0.2 is 0.05. So approximately 4.2 is about 0.05 larger than 2. So again, we were looking for the difference in the function value, so I used the first equation. Okay. Next one, let's approximate the cube root of 8.15 by finding the linearization of f of x equals the cube root of x at x equals 8. So we're trying to approximate the cube root of 8.5. Now this is the second type of problem we're talking about. Here we're trying to approximate a function value. So to approximate the function value, the first thing we're going to do, find the equation of the tangent line, then plug in the point that I want. So I need to find the tangent line. Well, the answer is going to be y equals mx plus b. The first thing I'm going to do is find m. So m here is f prime of 8, and we're finding the tangent line at x equals 8. Well, f prime is going to be 1/3 x to the negative 2/3. If I plug in 8 to this function, I'll get 1/3 times 8 to the negative 2/3. So let's see, what is 8 to the negative 2/3? It's going to be 2 to the negative 1/2. So let's plug this into our calculator. So 8 to the negative 2/3 times 1/3 is approximately 0.383. I believe that's what we get. Oh, nope, did that wrong. 8 to the negative 2/3. Gosh. 1/12. Yeah, plug that in wrong. So the slope of my tangent line is 1/12. Now, I'm going to write that down. Now I need to find b. In order to find b, you're going to use the point 8 f of 8, which is 8, 2, when I plug an 8 into my function. So I'll set up the equation y is 1/12 x plus b, so 2 is 1/12 times 8 plus b. Now I'll solve for b by subtracting the 8/12. So b is 4/3, which tells me that y is 1/12 x plus 4/3. What are we going to do at this point? Well, I found the linearization, I found the equation of the tangent line, so to approximate the cube root of 8.15, I'm just going to plug in 8.15 to my line. So all I'm doing is plugging it into my tangent line. So I'll get 8.15 times 1/12 plus 4/3, 2.0125. So pretty close to 2, but not quite. So again, we're trying to find the approximate function value. So to find the approximate function value, what we do is find the linearization, which is just another name for the tangent line, and plug in our value. Okay, another one here. Let's approximate sine of 0.2 by looking at the linearization of sine of x at x equals 0. So we're trying to approximate a function value by using the linearization. That means I find the tangent line at the given value 0, then I'm going to plug in the 0.2 that I'm looking for. So I need to find the tangent line at 0. So first thing is I'm going to find m. What's my function value? Or my function is sine. So to find m, it'll be f prime of 0. Well, what's the derivative of sine of x? Derivative of that would be cosine of x. Plug in 0, so I get cosine of 0, which is 1. Okay, so I found my slope of my tangent line. Now I need to find b. Remember, to find b, you're going to use the point 0, f of 0. Always go back to your original function. If you plug in 0 to sine, you get 0. So at this point, my equation is y equals 1x plus b, or just x plus b. Now I'm going to plug in the point 0, 0, so I get that b is 0. That tells me that the equation of my tangent line is going to be y is 1x plus 0, so just x. Alright, so I found the equation of my tangent line. Now I'm going to actually answer the question. Sine of 0.2, I'm going to be plugging in 0.2 for my x value to my tangent line. So if I plug in 0.2, all I get is 0.2. So that tells me that sine of 0.2 is approximately 0.2. So those are the two types of problems that you're going to see in this section. You're either going to have a difference in function values or actually finding the function value. Now along with those, what I can do is find the error. So again, all these that we're doing was, they were approximations. We want to know how far off are we. So the percent error, we always write it as a percent, is the absolute value of, the denominator here is the actual answer. I'm not going to write this in really technical math terms here, but it's going to be the actual answer over how far were we off. Or sorry, how far are we off over the actual answer. That's going to be our error. So let's do a couple of these examples. One of the examples that we did, we said that sine of 0.2 was approximately 0.2. that was the last one that we actually did. I want to know how far were we from the real answer. So what was our percent error? So what is the error? Well, what's the real answer? Sine of 0.2, if you plug this into your calculator, you get 0.19867. And I'm going to go to a lot of decimal places here because we want to know a pretty accurate error. So our actual answer was 0.9867. So that means that our error is 0.19867 in the denominator. In the numerator, I'll have 0.19867 minus my 0.2 that I guessed. So I'll get 0.19867 minus 2 in the numerator, divided by 0.19867. Oops, 0.19867 minus 0.2. This gives me the absolute value of negative 0.0067, which is 0.0067, but we always write this as a percent. So this is 0.67%. So to find the error, you're going to find out what was the actual answer that I was looking for. And then in the numerator, you'll say, how far was I off? So what was the difference between the actual answer and my answer? So let's do another one of these. The example that we did, we said that the cube root of 8.15. We got that was about 2, but it wasn't quite 2. It was approximately 2.0125. And I want to know what's the error. So how far were we off? So again, the error is going to be the actual answer. So what is the cube root of 8.15? It's actually 2.8548. The difference that we were off is 2.8548 minus 2.0125. So the real answer minus what we got. So let me subtract this out. 2.8548 minus 2.0125, all divided by 2.8548, gives me 2.295. What is this in terms of percent? 29.5%. So we were off by quite a bit on this one. On the last one, we were only off by 0.67%, which is not far off at all. This one, though, we were off quite a bit. So the percent error, what you're going to do is find the real answer that you wanted, and then find out how far were you off. Let's maybe do one more of these. Let me see. The first one that we did, we said that the change from x equals 2 to x equals 2.1 for f of x equals x squared is approximately 0.4. That's what we said. And if you go back to the first example that we did, that's what we found. Let's find our error. Well, what was the actual change from 2 to 2.1? Well, if I plug in 2.1 to my function and then subtract what I get when I plug in 2, I get 0.41. So this is the actual answer. The change from 2.1 to 2 in my function was actually 0.41. So I'll put this in my error. So I get 0.41 minus 0.4 divided by 0.41, which is 0.0244. So 2.44%. So even when we were doing the change in f, you can still find the error, find the actual change in f, which came from plugging in my two values to f, subtracting them, then plug it into my error. Okay, I want to do one more example here using linear approximations. Let's say that the population of mice is given by dp dt is negative 0.2 times p minus 100. Now, dp dt, this is talking about the change, the rate of change of the population. P is the population, t is time. So the rate of change of the population is being modeled by this equation. Okay. After 5 days, the population is 80 mice. I want to estimate the change in the population over the next 2 days. Okay, so we're trying to estimate the population over the next 2 days. Ask yourself, am I looking for a function value, or am I looking for the change in the function? Here we're looking for the change in the function, so change in population. So what we want to use is that the change in the population is approximately the derivative times the change in x. So same function, only difference here is that our function is p, not f anymore. Okay, so we need to find an a value and I need a delta x. Well, we're given the fact that the population is 80 after 5 days, so that's where we're going to start. And then the change in t here, or change in x, I should have written a t here because we're talking about time. We're talking about the next 2 days, so the change in time is 2. Now to do this, I need p prime of 5 times 2. Well, what is p prime of 5? Remember, another way to write p prime is dp dt. So this is just different notation, so dp dt, well, we have an equation for that. So it'll be negative 0.2, but not 5 minus 100. Right, 5 is a t value. We need to plug in the population at 5, which we were given as 80. And then I'm going to multiply the whole thing by 2. So this will be negative 0.2 times 20 times 2. So minus 8. Oh, I meant to put a negative there. It should have been a positive 8. So 0.2 times 20 times 2. So 8 mice. So again, we were looking for the change in the population. This is talking about a change in a function value, so we use this equation. P prime is the same as dp dt. The a here was a t value, but whenever I plugged it into my equation, this was not asking for a t value, it was asking for p. So I just plugged it in, found p prime of my a value, and then multiplied it by the change in t, which was 2. So over the next 2 days, you can expect the population to increase by 8 mice. So the estimate is for the population to increase by 8 mice. So that's kind of a real-world application for how to find or how to use linear approximations. Now this model is used a lot in biology. This is not some made-up model. We actually do use this a lot. So that's linear approximation. Just ask yourself which of the two types is it? Are you looking for an error or not? And then plug it in from there.